We want to find an equation for the propagator for one particle interacting with the other particles of the many-body system. One such equation was proposed by Dyson and can be derived using Feynman diagrammatic techniques. Feynman rules are more or less similar to what we had in the case of relativistic fields. In particular, the interaction part of the Lagrangian contains 4 fields, and therefore we will have 4 lines connecting to a vertex. And the value of the vertex is just g. And because we are dealing with an interaction which is instantaneous, we often have in the propagator the same time argument for both x and y. In that case, we change the second time into a t plus, and therefore we know how to apply our propagator in terms of phi dagger or phi dagger phi. The propagator for one particle interacting with its surrounding particles is represented by a thick line between the two space-time components x and y. The free propagator, however, where there is no interaction, d naught, is represented by a thin line. We can then write an expression for the propagator d as function of the free propagator d naught using interaction vertices. All the diagrams which have vertices make up what we call the self-energy. We also define the proper self-energy, which is the sum of the diagrams which remain connected when we cut one of the internal lines. We see in particular that a diagram like this one cannot be part of the proper self-energy, because if we cut this internal line, we end up with 2 disconnected diagrams. Plenty of the diagrams which are part of the proper self-energy involve interaction within the internal lines themselves. All these diagrams have very famous names, like the leaf diagram, the rugby ball diagram, the goggle diagram, the double leaf diagram, very original, the mouse diagram, and the saint diagram. These diagrams describe the fact that the internal line can interact with the particle of the medium. So all these diagrams can be replaced by the leaf diagram, but with a thick line. And the same is true for all the internal lines of the other diagram, so we can replace all these lines by a thick line describing a propagator for a particle interacting with its medium. The reason why the proper self-energy is useful is because the self-energy itself can be built with insertion of this proper self-energy. This means that the self-energy can be written as a sum of the diagrams which cannot be divided in 2 by cutting an internal line, plus the diagrams which can be divided in 2 by cutting one internal line, etc. Subbing this expansion into the expression for the propagator, interestingly, we recognize an expression for the interacting propagator itself. This is Dyson's equation. This is a self-consistent equation giving an expression for the propagator as function of itself, and therefore it cannot be solved directly. However, it is a good starting point for many-body perturbation theory. We see that the proper self-energy involves sometimes vertices which are different positions in space-time, and these vertices can happen anywhere. Therefore, we have to integrate over z and z dash. These 2 equations in the diagrammatic form and in the mathematical form are formally equivalent. Finally, we can apply a Fourier transform in the time domain in order to express the Dyson equation with propagators as function of energy.